In an addition reaction, two reactants come together to form one product. A typical example is the addition of a hydrogen halide to an alkene to form what is called an alkyl halide. In this reaction, X is either chlorine, bromine, or iodine. R is again a generic carbon-containing group. Looking carefully, one atom has been added to each carbon, an extra hydrogen to the left carbon, and a halide to the right carbon. So how does this reaction work? Let's diagram it. We start with the Lewis structures of the alkene and HX. Knowing that double bonds can act as Lewis bases, providing electrons for a new covalent bond, we suspect the alkene would be the Lewis base, making HX the Lewis acid. Since the acidic site on HX would be the electron deficient site, the new bond would prefer to go to the partially positive hydrogen. We'll diagram that with a curved arrow, starting at the double bond and the source of electrons and pointing toward the hydrogen. Of course, if that's all we did, hydrogen would have two single bonds around it. So to maintain the duet of electrons around hydrogen, the electrons in the HX bond will stay behind on X, and we'll diagram that too. The result of this first step of the reaction is a new entity that has a carbon-carbon single bond and a positive formal charge on the right-hand carbon. We also have an X anion nearby. It's not too hard to imagine what happens next to get to the final product. The X anion can act as a Lewis base, providing a pair of electrons to form a bond with the electron-deficient carbon atom. We can diagram that with a curved arrow, starting at a lone pair of electrons on X and pointing to the carbon atom. The result of the second step is the final product. You may ask why the H bonds to the left-hand carbon and X to the right-hand carbon. If we turn HX around, would it bond the other way? No. This reaction follows Markovnikov's rule, one of the many rules that you may learn in organic chemistry to help predict products. There are going to be accompanying shape changes at the two carbons, which we can see more clearly in this animation. We have at the top the alkene. You can see the carbon-carbon double bond between the two black carbon atoms. At the bottom we have an HX molecule, where H is the blue sphere and X is the green sphere with three lone pairs on it. As we start the animation, we have the double bond converting to a single bond, and that pair of electrons is the source of the new bond between carbon and hydrogen. And the old HX bond is converting now to a lone pair that will stay behind on X. You also see a negative charge developing on X and a positive charge developing on the right-hand carbon of the original alkene. We'll continue this. So we form the new CH bond. Let's stop for a moment and notice on the left-hand carbon we now have tetrahedral geometry, whereas on the right-hand carbon we still have the trigonal planar geometry. As X approaches the positive carbon, a lone pair is converted to a bonding pair to form the new CX bond.